when we're dealing with geophysics, we're dealing with physical property contrasts. And so we've already dealt with density with gravity, seismics, you deal with acoustic impedance, resistivity, you deal with resistivity or conductivity, they're the same thing, just the inverse of each other. And we've mentioned that magnetics is susceptibility. And so very important is that you can't do modeling with the software until you know the susceptibility of rocks. And so this is an instrument that you would use when you go on field school and you collect samples and you take measurements from them. You can see it even has to be on a wooden table because you've not allowed anything magnetic around. So it's important to take these measurements. So these are just some examples from the Bushveld complex, just because that's where we usually do the field school. And so pyroxenite and chromite are very dark magmatic rocks, so anything that's been formed by magma. Dark usually implies that there's lots of iron and magnesium, and they've got high values, so anywhere from 20 to 80, and that one's about 20 to 50. With anorthosite and norite, you don't have to know these for the exam, you'll get used to these as time goes by. These don't have much iron or magnesium, and you can see the values are 20 or lower. And in density, we had values that were quite close, so like 2.2 to 2.9, I think granite was 2.5 maybe to 2.7, whereas these values can vary a hell of a lot more. So that's the one thing about magnetics, is susceptibility values are very broad. And this is even higher. So we were saying dolerite makes up an intrusion, a dye, and these values going up to the thousands. So Hangelite there, Hartsbergite is also a very dark rock, and it's also going up to 2,000. And you can see the units here, times 10 to the minus 6 CGS, or you either see it in CGS or just SI for SI units. So those are the two units that we use for measuring susceptibility. This is an example of a dye intruded into the ground. And you should all moan at me and say, no, but it goes deep and it shouldn't be cut off. And when you're taking measurements over a body, you're measuring two things, possibly three things. When you're measuring magnetics, you're measuring the Earth's magnetic field at that place. And so we all know that Earth's got a magnetic field due to the rotating core, and it varies over time. And then that field induces a field in this dye. And so the dye itself has its own magnetic field, or own field lines. And so this is what you would actually measure over a dye. So the field lines are coming out from the top of the dike and coming down here. So you can see at the top of the dike here, it's in the same direction as the main magnetic field. And so these two add together to give a big anomaly. On the sides here, they're in opposite directions. So they cancel out to give this low. And then at the back side here, they're in also opposite directions, and so we get this low here. And so this is what you would measure in the southern hemisphere. Well, this positive is always to the north. If you are in the northern hemisphere, it's actually flipped around, and this peak is always towards the south. So the way you can remember it is that this peak is always towards the equator. So it's towards the south in the northern hemisphere, because the equator is towards the south, and in the north in the southern hemisphere, because the equator is towards the north. So that's just something that you can remember. So if you've got a steep, you dip in dark, it will have a negative and a positive. So when you see a magnetic map and you see this positive, the body is not directly underneath it. It's slightly shifted to be between the negative and the positive. We spoke previously, and we've spoken today already, about how often to measure. So you can see if I measured at all these red spots, that's the anomaly I would get, because I'm completely missing out this positive. So I should try and measure, obviously, at the yellow spots, and I'll get a bit more of an angular anomaly. This was where you use the word the Nyquist frequency. This calculation to determine how often to sample. And I think it was 2 times your highest frequencies in the data. So when you're doing magnetics, you can either do a ground survey, or you can do this aeromagnetic survey. So you can fly, or you can do the ground. So knowing what you know from gravity, why would you choose to go on the ground compared to in the air? What changes? You're further away from the body, so what changes? Does anyone remember?
Resolution.
Yes, the word resolution is a good one. Remember we said for gravity, that the further away you are from the body, the effect due to gravity decreases. So we said even on the Earth, as you get into higher topography, you're further away from the center of the Earth, so the pull of the Earth is less on you. And it's very similar for magnetics. The further away you are from the body, the lower the magnetic response from the body. So to go higher up, your anomalies become smaller, but to be in an aeroplane, you're going to go a lot quicker. So there's a trade-off. Again, it's about money and it's about time. Ground data is more expensive and higher resolution. This is what it looks like. Our magnetometer is slightly different, but you have a magnetometer, there's a GPS. Our GPS isn't on the hat, it's on the side, and data storage unit. And so the nice thing with this magnetometer is you literally can walk. You just walk and it records as you're walking. Whereas the older magnetometer, which we also have, and you'll also use in field school, you have to walk 5 meters, put it down, take a measurement. Walk 5 meters, put it down, take a measurement. You can't have anything magnetic on you. I, by accident, once did a survey with a hat that had a magnetic rim, and I didn't realize it, and the data was a disaster. So we had to redo that one.
In the case of aeromagnetic data,
so what they do is they fly over geological bodies and they collect magnetic data. And the line spacing is 1 kilometer. So literally you're playing through north to south and then south to north 1 kilometer further away. And so this here, this outline, is Transvaal sediment, and these rocks here are part of the Bushveld complex, so they're also very magnetic. The Bushveld complex was this magma intrusion into the Earth, and so obviously you would expect a few of them to be magnetic. And these lines here are the dikes in this area. So you can see quite highly magnetic as well. And then this is a comparison here of ground magnetic data, so the red one, and then the airborne data, the blue. So it's completely the same area, the same line. But you can see because they're in an aeroplane, maybe 100 meters up off the ground, this is the resolution that they got. So this anomaly, you can see, is practically reduced by like 500 nanotesla. The SI unit for magnetics is nanotesla. And so you can see here, by going in an aeroplane, you don't even pick up these 2 dikes. You probably wouldn't even know that there were 2 dikes there. So there's a trade-off. You're getting fast data, but you're losing some of the geological information. Okay, we've done this already, so forward modeling, we did in Grav 2DC, but there's also a MAG 2DC. And so this is an example of a dike, and you can see here this negative and this positive. And so where's the equator, or where's north? The peak is always towards north. And this is similar to what we were doing the other day in Grav 2DC, about fitting, you put the body in to try and fit it to the data. So before the field work, remember we said this, that before you go into the field, you want to plan how big the anomalies are, how often I must take a measurement. So that's why we do this modeling. That's why the software is so powerful. You want to make sure you're using the right equipment. Remember we said that the CG5 gravimeter has a sensitivity of 0.04. The magnetometers, you're looking at much higher values, but like 10 nanoteslers. So it's a much larger value. Magnetic values are bigger than gravity values. Should you change your station spacing? So it's all about planning. After field work, you use the software to model your data. Ambiguity. We saw the other day that everybody put a circular anomaly into Grav 2DC. We all had to say which model had values bigger than 0.04, and we all gave different answers. And it was because we all had different models. And that's what we mean here when we say ambiguity, is that you can get data from the field, but if you model it or if you model it, you might give a completely different geological interpretation. So that's why you need seismic data and borehole data to tell you how deep are you expecting the body to be, how thick, and that you can actually take samples and measure the susceptibility.
to try and reduce the ambiguity.
Okay, so what can you test in MAG 2DC? Acquisition height. So this is the height at which you collect your data. So usually if you're holding the magnetometer, it's a meter or 2 meters. So here, we've got a profile at a bearing of 0, so that means I'm going north to the north. I've got a dike here, this is a dike, dipping at 90 degrees. The body depth, you can't really see it here, but it's 5 meters below the surface. It's got a width of 5 meters, a susceptibility of 0.01, reference height 2 meters, maximum depth display, that's the same as grad 2BC, 2,000 meters, oops, more like 1,000, and intensity, these values here, intensity, inclination, and declination, these are values describing the main magnetic field where you do your survey. Remember we said when you're doing the survey and there's a body, it has an induced field. So the magnetic field of the Earth is creating a field in this body. So we need to know what that main field is so that we can estimate what this induced field is. So I need to know these values, you get them off online. So this is for at where I'm doing my survey, it depends on your latitude. I get intensity and inclination and declination. Inclination is the angle at which the field lines are coming into the Earth when you're doing the survey, and declination is the difference between true north and magnetic north. We're changing our reference height. So our anomaly here is at 200 nanotesla. As I get higher to 15 meters, I'm already down to 80. As I go to 30, we're about 40, 50 down to 20, 80 we're already by 1 point something, 100 just by 1, under 1. So this is where you'll be flying in a plane. You're going to have an anomaly of 0.5, whereas if you're on the ground, you're going to have an anomaly of 200 nanotesla. So that's quite a big difference. So you just got to decide what's best for your survey. Okay, the dip angle. So you can see already this anomaly has changed. You're expecting a positive and a negative, but because of this dip, you've lost that negative. So let's see how it changes as our body moves towards vertical. We can see there's much more of a negative when it's vertical, and the negative disappears as it dips upwards. So magnetics is a bit more complicated than gravity, although we saw this in gravity as well. As the body dips in gravity, there was an image I showed you, it makes the anomaly less symmetrical. So yeah, we're adding more of a negative as it's becoming vertical. Different station spacing. So on the top right-hand corner, it's station spacing of 1. So we're making a measurement very often. Station spacing of 5, 10. We can see our anomaly at 100 meters. So here we're taking a measurement every 100 meters. Now why does it look like that? If we go back to our station spacing of 1, if you're taking a measurement every 100 meters here, that's what you're measuring if you're taking a station spacing of 100. We kind of lost this peak completely.
Because you've lost this peak, your amplitude should change as you increase your station spacing.
Again, an example of aliasing. So the word Nyquist frequency and the word aliasing are used close together. So you use your correct Nyquist frequency to avoid aliasing. And this is an example of aliasing. So you haven't taken enough measurements, and so you've got an anomaly that is not a replica of what's actually there, because you've lost data because you haven't sampled enough. So it's caused aliasing. Number of bodies is also something you can play around with. So here we've got 2 dikes, exactly the same. The bodies are separated by 60 meters here. We're just looking at a different reference height. So we had a reference height of 2, we can see the bodies. If we had a reference height of 15, you can see they're starting to merge together. 30, you can kind of see there's another dike. At 50 meters, you don't know that there's 2 dikes. So if I was flying at 50 meters, I don't know that there's 2 dikes there, and so forth as you get higher and higher. Oh, this is not station spacing, it's separation. So as we move in closer and closer together, at some point their signals are going to merge. So you can see at this point here, if I start getting closer and closer together, it's going to get harder and harder to recognize that there are two darks there. And by this point, it's already, we'll just say that there's one. Very important in magnetics is to record what direction your survey is in. Because if it's south to north, you're going to get a negative in the south, a positive in the north. If it's west to east, it changes somewhat, and you're getting a positive towards the west and a negative towards the east. Obviously, if you go north to south, it swaps around, and it swaps around there. So magnetic gravity was simple. You could go any direction, and it wasn't a problem. Magnetics, it's dependent on your latitude, and it's dependent on the orientation of your line. You must add your bodies in a clockwise direction. I started saying that in Grav 2DC just to get you into it. If you add it in the wrong direction, if you go anti-clockwise, your anomaly will flip, and it'll be wrong, because it's important. So that's an example of it done in an anti-clockwise direction. I want you to do for me two darks that are 20 meters wide at a depth of 10 meters. They're both the same, and they're 100 meters apart. Can you resolve both darks? Can you see them? What happens if the darks move closer together? You know what's going to happen? Okay, so it says to you, top left, profile bearing, so it's 0, means that you're going toward the north, which is fine. Next one, reference height is 1, so it's 1 meter, so that's if you're holding the magnetometer. Third one, maximum depth to stay 100, you can leave that, that's fine. Next line down, geomagnetic field parameters, that's the one I told you about, that's the main magnetic field. So intensity is 28,000, it's approximately right for South Africa. Inclination is -60, because the field is coming into South Africa at an angle of -60 degrees. And in South Africa, the declination is different between true north and magnetic north in South Africa. It's about -22. So you can leave all of that. Initial body susceptibility 0.01 is fine. You can uncheck read in field data. So at the bottom, because then it makes station spacing and number of pairs, you can leave it at 10 and 100. Strike length, change your strike length to 1,000 because we're dealing with darks, so they're in and out the board. And you can leave your susceptibility as SI and change your units to meters. And click OK. And now again, it says click, 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 and then right click to close your body. So give me one dark. And the second dark, remember we said how to add a body. You go edit the menu.
And you want a strike length of about 1,000 coming in and out the board. And again, click, 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 and right click to close.
It will be 20 meters wide. So if you double click on the body, it will tell you how wide it is, and you can change that. And then you'll be at a depth of 10 meters.
And you can check this for the second body as well. Change it to 20 meters width and 10 meters depth, and click calculate to update the curve, or click OK. Another thing you can do is copy. So go edit the model, copy a body, and then you're going to say your horizontal displacement, how far off you want it to be moved. Vertical, do you want it to be shift up or down? So leave that as 0. You can see here you've got a second body. Let's delete it. Go edit the model, delete.
What I would like you to do now is to go edit the model and move a body, and tell me how close together you lose the fact that they're two darks. So when do they merge together?
As you get closer, you can change the horizontal displacement to a smaller value like 5, and then move it at smaller increments. And then you can see at what point the two curves merge together. You can actually calculate the exact distance between the two dikes by going edit the model and change the corner numerically. And then you just need to click next corner or previous corner to determine what the top right corner is on the left hand body. And so you can see in next corner that's at 288 is the horizontal distance. And then also what the top left hand corner is on the right hand body, so that you can determine the distance between the two dikes.
To show you guys how complicated magnetics can be, I want you to have two DC windows. The first window, when you start your model, I want you to choose a bearing of 0. So that's what direction are you walking? 0 is north. Second window, I want you to have a bearing of 90, which means you're walking towards the east. And then in both of them, I want you to just put a dark and compare what they look like. Once you've compared them, I would like you to try and change the dip, because initially they should be different, and we want to try to see if by changing the dip we can get the anomalies to look the same.
So on the left here you can see a profile bearing of 0, and I'm going to choose SI units and meters, and then unclick read and field data and click OK, and then we click to add a dark, click, 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 right click, and then over on this right hand window I'm going to begin a new model and change the bearing to 90. SI, meters, read and field data, okay, click, 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 click. You can see the difference in the profiles because of the bearings. And now I really just want to change the dip of this profile on the right to see if it ever looks like this profile on the left. And so this is the dip in degrees, so I'm going to change it by 10, and so we're going to see, is it ever that the negative is in the south here and the positive is in the north? And you can see as it turns it warps the body slightly, but you can see that it's never the case that it looks like a north-south profile. And you could do the same if you wanted on this one here. Try rotate it and see. But yeah, even though you're tilting the body, they never actually have the same anomaly.